Hi everyone. In this video, we'll be talking about finding volumes of a new type of three-dimensional solid called a solid of revolution. In particular, in this video, we'll learn about this new type of solid. We'll use ideas of slicing that we saw previously to derive integral expressions for the volumes of those solids. And we'll work to understand the mathematical consequences of different region geometries on their resulting solids of revolution. So in this video, we're actually going to just take learning about this through sort of 4 different examples. But before we jump into those examples, we first want to do a quick definition of what a solid of revolution is, understand what these things are, what these objects are, do a little bit of geometry review, and then we'll jump into those examples. So a solid of revolution is a three-dimensional solid that's created when a region in the plane is rotated about a line. So let's first think about the solid of revolution that's created when the region bounded by y is equal to 1 minus x squared, x is equal to 2, and y is equal to 1 is rotated about, in the first case, let's imagine it's rotated about the line x is equal to 2. Well, to make sense of this first, I first have to make sense of the region. So if I were to sketch this region, or you could use Desmos or something to help you make sense of this region, you get a region that looks something like this. You'd have this line would be y is equal to 1. You'd have this line x is equal to 2. And this would be your function y is equal to 1 minus x squared. So the region you'd be looking at would look something like this. And now you want to imagine that that is rotated about this axis, which is the line x is equal to 2. So in this case, it's rotated about this line. Now, if I were to rotate in that fashion, right, you can probably sort of imagine I'll get a figure that looks something like this. It's going to look sort of like maybe some sort of distorted cone. So it's, again, imagining taking this, flipping it out and rotating it around in 3 dimensions, right, out of the plane. And I'll get a figure that looks something like this. Okay. I could also generate a different solid of revolution by just thinking about rotating this around a different axis. So maybe instead of rotating it about the line x is equal to 2, maybe I rotate it about the y-axis. Now, if I rotate it about the y-axis, so now sort of think about it coming out this way, on the very bottom, I'm going to have sort of a flat, or sorry, on the very top, this is going to be flat because this portion of the region touches the axis of rotation. But then the rest of this is almost going to be shaped something like a bowl. So if I sort of think about, so here's my axis of rotation, I'm going to get this sort of 3-dimensional figure, which is going to look something like right, something like this, and then rotated around. So I'm going to get sort of a bowl, right? You can imagine this is sort of a bowl that's turned upside down. So you have the, sort of the inside part of the bowl, but then the bowl has sort of flat walls on the outside. You know, it's turned upside down, so it's flat on top. But I get this shape that sort of looks like an upside down bowl. It's sort of empty on the inside here. The solid part really are the walls of the bowl in here. Okay. Now, you know, these things are a little difficult, right, just to even visualize. But now I'm going to want to be able to find their volume. So one of the things I want to highlight that's really convenient about these, though, is that if I were to take cross sections of these, of either one, so let's imagine first I was to take a cross section of this. If I were to take a cross section of this, I would get something that looks like a little cylinder, right? A little disc, okay? If I were to take a cross section of this, okay, I would get something that looks like a disc, but with another little disc removed inside. So the book often refers to these as washers, right? You can sort of think of them as donuts, but it's really like a cylinder with a little cylinder inside removed. Okay. And the nice thing is that no matter where I take this cross section, I get a piece that fundamentally looks like this. Now, the size of things may change, but wherever I take a cross section here, I'm going to get a washer. And wherever I take a cross section here, I'm going to get a disc. And so just like we did in the previous video, if I have a consistent cross-sectional shape, then I ought to be able to find the volume by integrating. And so that's going to be exactly the idea. Now, before we jump into an example, let's just quickly think a little bit more about these particular shapes we're looking at, right? So we know that we're going to need to understand washers and discs. You could worry that maybe there's other shapes you need to understand well, but it's really for solids of revolution, it's really those two shapes that you need to be able to understand. So just very quickly, right, let's remind ourselves we're going to want to be able to find volumes of both of these shapes. So just quickly as a reminder, right, if I have a disk, right, the word disk is really the same as cylinder, right? And so if I have a cylinder, it has some radius r and some height h, then its volume is pi r squared h. Okay. If I have a washer, well, again, a washer really fundamentally is just a cylinder with another cylinder removed. So you can sort of imagine, right, there's this hole sitting here in this other cylinder. So here, I want to imagine I have some inside radius. That's little r is sort of that inside radius. And then I have some outside radius, right? And so if I think about the volume of this, it really ought to be the volume of the big cylinder. Now, if I just did pi capital R squared h, so I have some height here also, right? This would give me the volume of the whole cylinder. But then I need to subtract out the volume of this smaller cylinder, right? Because that is missing, right? And so if I factor a pi out front and an h out to the end, then I get the volume of this washer being pi times big radius squared minus small radius squared, or sometimes say outside radius squared minus inside radius squared times the height. Okay. So it's nice because we can find volumes of these little shapes, which are the cross sections. And if we add them all up or integrate them, right, then that should give us the overall volume. All right. So let's take a look then at a couple of examples to get started. And we're going to start by looking at ones whose cross sections are disks. All right. So to begin with, we'd like to find the volume of a solid of revolution generated by revolving the region bounded by the graph of y equals x cubed, the x-axis, and the lines x is equal to -1 and x is equal to 2 about the x-axis. In any one of these problems, the first thing we need to do is we need to generate a sketch of our region. Okay. So here we're going to start. We're going to take the graph of x cubed. And so that's my x cubed. I have the x-axis. Okay. That's sort of easy because it's just already sitting there. The line x is equal to -1. It would be like this. And then x is equal to 2, which would be over here. So the region we're looking at is sort of the shaded in region here. Okay. And now you want to imagine, now that we understand our region, it's going to be rotated about the x-axis. Okay. So it's going to be rotated around this axis here. So if you think about sort of, okay, as this is rotated around, it's going to split out this way. And this piece, as it's rotated around, is going to sort of split out this way. Okay, and you can sort of start to imagine that you're going to end up with this shape that's going to look something like this. You're going to end up with this sort of horn shape, right? So you have sort of a smaller circle over here, a bigger circle over here, and then it's sort of pinched in a bit in the middle. And it's not quite symmetric, really, because these x is equal to -1 and x is equal to 2 aren't symmetric about the y-axis here. All right, so this is what my solid is going to look like. And now, again, I want to start thinking about, okay, well, what if I were to take cross sections? Now, I could cut either way, right? And we've seen this before, right? You can sort of make slices either way. If I make slices this way, right? I make sort of horizontal slices, it's not clear what my cross sections would really look like. But if I make my cross sections vertically, so notice that's perpendicular to the axis I'm rotating about. So if I make my cross section this way, right? Then when I come over here, right, my cross section here, I imagine cutting here, my cross section is going to look like a disc of some sort. Now, the first thing I want to do is I want to think, what's the volume of that disc? Now, certainly the volume of that disk is going to depend on the x value where I take that cross section, right? If I take the cross section, say very close to x is equal to 0, I'm going to get a very small disk. If I take it closer to x is equal to 2, I'm going to get a much larger disk. Okay, but in general, the volume of a disk, right, is pi r squared h. Okay, now in this case, my h, because I'm taking a slice this way, my height here really is like a little slice of the x-axis. So we're going to call that dx. So my height is dx, and now I just need my radius. Okay, so what would the radius of this disk be? Well, it's really the distance from the center. Well, the center is my axis of rotation, or the x-axis, to the outside of my function. So here, it's really just, get a slightly different color here. It's really just this height right here, okay? And that height is just the y value of my function, which is just x cubed. So in fact, here, my radius is just x cubed. So the volume of my disk is pi times my radius, which is x cubed, squared, times my height, which is dx, or pi x to the 6th dx. Well, now that I have the volume of this disk, I just need to add up all of these disks. And so to get my total volume, then I want to integrate across my entire range of x values that are creating my solid. So my x values are ranging from, this was x is equal to -1, this was x is equal to 2. And so I want the integral from -1 to 2 of, now I'm going to add up the volume of each of these little disks. So pi x to the 6th dx. Now this is a very nice definite integral that I can compute. So I'll factor out the pi. The antiderivative of x to the 6th is x to the 7 over 7, evaluated at 2 and -1, and take a difference. So this is pi times 2 to the 7th is 128 divided by 7. Minus, if I evaluate at -1, -1 to the 7th is -1 over 7. And so I end up with 128 plus 1 over 7, or 129 sevenths times pi. And there's the total volume of my solid of revolution. All right, let's try this again with another problem. Imagine you're now asked to find the volume of the solid of revolution generated by revolving the region bounded by the graph of y is equal to x cubed, the y-axis, and the lines y is equal to 1 and y is equal to 8 about the y-axis. So a lot of this may look sort of similar to the previous problem, but as we'll see, the geometry of everything changes as we change our axis of revolution and some of the bounds. So again, we'll begin by sketching a graph of our region. Okay, so our region is the region bounded by x cubed. The lines y is equal to 1 and y is equal to 8. And the y-axis. So I sort of go back and look at this. Right here is my region here. So here's my region R. And now this region is going to be rotated about the y-axis. So you can sort of imagine now as I rotate this about the axis, I'm going to end up with something that'll look more or less like a bowl, except it'll be solid inside, and it'll be flat on the bottom. Okay. So I'm going to end up with a solid that looks something like this. Again, this curved part here forming the sides of the bowl, flat bottom, flat top. Okay. And so my axis of rotation, right, is this. I sort of imagine this is my y-axis here, which is my axis of rotation. All right. Now again, I need to choose how I'm going to slice this, and I want to slice it in a way that's going to give me consistent cross sections. If I start slicing like this, it's not clear that I'll get a consistent cross section. In particular, if I start slicing over here near the edge, my bottom is going to be on the curved part. When I slice near the middle, it's going to be on the flat part. I'm going to get these sort of irregularly shaped cross sections. Okay. However, if I slice horizontally, right, then I should get very consistent cross sections, right? So if I slice this way, then every time I take a slice, I should get out a disk. Let me actually draw that below this time. So when I take that here, then I'll get a nice disk. Okay. Now, of course, the question is, what's the volume of that disk, right? And so in general, the volume of a disk is pi r squared h. Now this time, because I'm making my slices horizontally, my slice is like a little piece of the y-axis. So my height here is going to be dy. Okay. And now what I need is I need the radius of this disk. Now the radius of this disk is going to be the difference between the distance between the y-axis and the outside part of this bowl. So coming back over here, I really want to know for a given y value, right, because this distance changes as the y value changes. For a particular y value, what is this distance? Well, this distance is really just the x value that lies on this curve. So since this curve was y is equal to x cubed, we can solve this for x. We'll get x is equal to y to the 1/3 power. Oh, sorry, I've written up there a bit, so let me. So this curve, right, is y is equal to x cubed. And so solving for x gives me x is y to the 1/3. So this point is at, for a given y value, this x value is y to the 1/3. So this distance between the y-axis and the outside is y to the 1/3. That tells me that my radius here is y to the 1/3. So the volume of my disk then ought to be pi times my radius, which is y to the 1/3 squared, times the height, which is dy. Simplifying a bit, I get this as pi y to the 2/3 dy. All right, now that I've got the volume of one of my cross sections, and again, these are consistent cross sections, I can now just add them up by integrating to get my total volume. So pi y to the 2/3 dy. Now I need to ask myself, over what range of y should I be adding up these cross sections? Well, I ought to be adding here from y is equal to 1 up to y is equal to 8. And now again here I have a very nice expression for the total volume. So if I factor the pi out of this integral, antiderivative of y to the 2/3 will be, I'm going to increase the power by 1, so it'll give me y to the 5/3 divided by 5/3. Dividing by 5/3 is the same as multiplying by 3/5. And I'm going to evaluate that at 8 and 1 and take a difference. Okay? So this will give me pi. This will give me 3/5 pi times 8 to the 5/3 minus 1 to the 5/3. Okay. Now 1 to the 5/3 is just 1. 8 to the 5/3, that's the cube root of 8 to the 5th. Okay. So this is 3/5 times pi times, now 8 to the the cube root of 8 is 2, and 2 to the 5th is 32. So it's 32 minus 1, or 31. So if that's 31, and then I'm going to multiply by 3. 31 times 3 is 93/5 pi. And so there is my final answer in terms of the volume. Okay. So again, here in these first two examples, what we've seen, there are two examples where we get cross sections that are these consistent disks. In one case, we cut vertically. When we cut vertically, that gave us a cross section that had sort of height dx. And then we were able to write out our integral. In this case, when we cut horizontally, that gave us a height that was dy. But again, we were able to go through everything here. And what I want to emphasize is that the direction you cut should always be perpendicular to the axis of rotation, right? So in this case, my axis of rotation was vertical. It was the y-axis, so I cut horizontally. In the previous example, my axis of rotation was horizontal, so I cut vertically. Okay, so that's sort of a key there in determining which direction to cut. Once you do that, that's going to tell you sort of what variable you need to be dealing with. All right. Now, in these next two examples, we're going to see we get a slightly different cross-sectional shape. Okay. So in this case, I want to find the volume of the solid of revolution generated by revolving the region bounded by the graph of y is equal to x squared, the x-axis, and the line x is equal to 2 about the y-axis. So again, we're first going to start by sketching our region. Okay. So our region here, we're going to have y is equal to x squared. The x-axis, so again, that's this piece down here, and the line x is equal to 2. Okay. Our region is going to be this. Okay. And now we're going to rotate about the y-axis. Okay. So now our axis of rotation will be this y-axis here. Now, as you can probably start to tell, when I rotate here, right, I'm going to get almost this bowl shape. So this outside portion, right, I'm just going to get these flat sort of walls rotating around the outside. But on the inside, I'm going to have this sort of bowl shape carved out. Okay. So if I go to sketch this after rotating, right, I'll end up, again, the outsides are going to look sort of flat. But then if you look inside, right, inside, you're going to see this sort of carved out bit. And again, that is curved. They're not flat. okay? And so you're going to get, you're getting this sort of, on the outside, again, the walls are solid, but on the inside, right, you have these sort of curved walls. You get this sort of, again, bowl shape for this solid of revolution. All right. Now, let's see. I want to try and find the volume of this. So I need to think about cutting, okay, and cross sections. Again, what's our rule of thumb? The rule of thumb is always cut perpendicular to the axis of rotation. The axis of rotation here was vertical, so I'm going to cut horizontally. Okay, so if I cut horizontally here, what's going to happen? Well, if I cut horizontally, I'm going to get a disc here. Okay, so or sorry, not a disc, a washer. Right? So you can imagine cutting here, there's this empty space from the bowl inside. So when you cut across here, you're going to get this empty space in the middle. Okay. So now if I want to find the volume of this, right, I already know the volume of this is pi times outside radius squared minus inside radius squared times the height. Okay. And looking at this, because of the way I've cut, my slice is going to be, my height is going to be a little slice of the y-axis. That's going to be dy. And now what I need to find are these inside and outside radiuses, radii. Okay. All right. Well, let's think about sort of translating this back over to our picture here, right? The inside radius would be like this distance here. And again, that's going to change as my y value changes, right? Okay. So let's see, that inside radius is just going to be the, for a given y value, it's going to be the x value that puts me on this curve. Well, this curve here was y is equal to x squared. So if I solve for x, that gives me x is equal to the square root of y. Okay, so this inside radius for a given y value is at the square root of y. So that's going to be my little r. The outside radius, well, the outside radius is going to be fixed, right? The outside radius is always the distance from here to here, and this line was the line x is equal to 2. So for any y value, my outside radius actually stays the same. It's always 2. So my outside radius will just be 2. And so now, plugging all this in, I'll get that the volume, sorry, I should be careful here. This is the volume. I'm going to put sub W for washer. So the volume of my washer is pi times the outside radius, which is 2, squared, minus the inside radius, which is square root of y, squared, dy. And now if I simplify this a bit, this is pi times 4 minus y, dy. All right, great. Well, now that I have the volume of my washer, to get my total volume, I just need to add them all up. Okay. But now I need to ask myself, over what range of y values do I need to add these up? Well, going back to my region, the lowest point of intersection here, we started with the x-axis, right? So that's y is equal to 0. All the way up to this y value. So I have to ask myself, well, what is this y value? Well, x is equal to 2 here, and it's also on this curve, y is equal to x squared. So this is y is equal to 4. Okay. So I'm going to integrate here from 0 to 4. Now, again, this is fairly straightforward in terms of the integration. So I pull the pi out. It's pi times the antiderivative of 4 is 4y, minus the antiderivative of y is y squared over 2. I'm going to evaluate at 4 and 0 and take a difference. Clearly, if I plug in 0 here, that just gives me 0, so I just have to plug in 4. We mean pi times 16 minus 4 squared is 16 over 2, which is 8. And I get a total volume here of 8 pi. All right, so this it's a little bit different because now my cross section is no longer a disc, it's now a washer. But fundamentally, the idea is the same because I can find this consistent cross section and express its its volume. I can then express the total volume as the integral of that and find the total volume in that way. And again, a lot of our rules of thumb remain the same, right? Notice again, I slice in the direction that is perpendicular to the axis of rotation. All right, let's look at one more example. And if you're sort of paying attention, you may be able to figure out sort of what we haven't sort of covered yet. And that's, we're going to do one more example where we're going to have a washer as a cross section, but this time we're going to be rotating around something that's horizontal. So we'll sort of slice in a different way. All right, so for our last example, let's imagine we want to find the volume of the solid of revolution generated by revolving the region bounded by the graphs of y is equal to x squared and y is equal to x about the line y is equal to 2. Now, there's actually something else that's a little different about this problem. This is the first time we've had an axis of revolution that's not either just the x or the y axis. So that's actually going to change our problem ever so slightly as well. But let's take a look at sort of what happens. Again, first step always is to sketch the region. Okay. So in this case, I have the graph y is equal to x squared and y is equal to x. Okay. And so you can sort of see here, right, I'm going to end up with this shaped region here. But now I'm going to rotate about the line y is equal to -2. Sort of imagine we're down here, and there's our axis of rotation. So now you can see this region doesn't touch the axis of rotation at all. So you're going to have sort of this empty space in between. Now, if you sort of think about what that would look like, okay, so you're going to take this region and then you're going to rotate it around. Again, I'm not an artist, but I do have a little bit of practice sketching these sorts of things. Okay, so you're going to get something that looks sort of like this. So again, you're going to have this almost sort of weirdly shaped donut. The outside is going to be flat, right, but angled, right? And the inside is going to be sort of curved. It's going to be curved, sort of going around the inside in here. Okay. Now again, just for emphasis, let's put our axis of rotation in a slightly different color. Axis of rotation now, right? So I'm imagining this is like y is equal to -2. All right. Now, I want to make a slice perpendicular to the axis of rotation. Axis of rotation is horizontal, so I'm going to make a vertical slice. Okay. Let's see what happens when I make that vertical slice. Well, I'm going to get a washer, right? I have empty space in the middle. I have some filled in stuff on the outside. So when I do this, I'm going to get this washer, but again, this one's going to be notice I have enough trouble drawing these in the usual orientations. Then when they flip over, it doesn't always. Okay. So sort of something like that, right? Washer, but on its side. Now, the height of that washer, right? Height is going to be, well, that's going to be a little slice of my x-axis. So that's going to be dx. And now what I'm going to need the inside radius and the outside radius. So the inside radius, right, the radius is measured from the axis of rotation. So the radius is going to be the distance from here, or the inside radius will be the distance from here to here, okay? Well, this distance, to figure out exactly what it is, it probably helps to break it down. So the distance from here to here is just 2, right? From y is equal to -2 to the x-axis, that distance is 2. And then the distance in here, right? So this distance depends on your x value, right? but it's on the line y is equal to x squared, so this distance is just x squared, okay? So this total distance here is x squared plus 2. So my inside radius is x squared plus 2. Now we'll do the same sort of analysis for my outside radius, right? My outside radius, again, will be the distance, say, from here to here. It'll be 2 as we go from the axis, from the axis of rotation to the actual x-axis. And then this height here will just be equal to x, because this goes up to the line y is equal to x. So the outside radius is x plus 2. Okay. So then the volume for my washer, right, is pi outside radius squared minus inside radius squared dx times height. Okay. And now to find the total volume, I ought to integrate this quantity. Now, before I do that, actually, let me come back over here and simplify this a bit. Okay. So if I were to sort of FOIL all this stuff out, what would I get? I'll get a minus, and again, I'm going to sort of skip some steps here. You may want to check this on your own. So I get a minus x to the fourth. I'm going to get an x squared and then a minus, so I get a minus 3 x squared. So here I'll pick up an x squared term. Here I'll pick up a minus from there, and then a 4x squared. So I'll have an x squared minus 4x squared. That gives me minus 3x squared. I will pick up here 2x. I won't pick up any just x terms here. And then let's see, here I will pick up a 4 minus, there I'll also pick up a 4. 4 minus 4 is 0. So that ends up being a simplified version of my volume. It's a little easier to integrate here, right? So my total volume then is the integral of minus x to the fourth minus 3x squared plus 2x dx. And now I need to figure out what range of x values do I want to integrate over? Well, I want to integrate over this whole range of x values. These intersect at 0 and 1. Again, this would be where x is equal to x squared, right? Because this is y is equal to x, this is y is equal to x squared. So it's where they intersect, which is when x is equal to 0 and x is equal to 1. Okay, so I'm going to integrate from 0 to 1. And so what do I get here? Oops, I forgot a pi. Let's see, since I forgot it, I'll go ahead and stick them there outside the integral. So I will get pi times, okay, take the antiderivative. This will be a minus x to the fifth over 5 minus x cubed plus x squared, evaluated at 1 and 0, and take a difference. So at 0, these will all be 0. If I plug in 1 here, I get pi times minus 1/5 minus 1 plus 1. And now we know for sure that we have made a mistake. And the reason we know that we've made a mistake is this is coming out to be negative, which can't possibly be correct, right? So let's see if we can go back and quickly identify where our mistake might lie. So let's just quickly check here. So here we would have gotten an x squared plus, oh, there's my mistake. I already found it. This should have been a 4x. And so this should have been a 4x. And so this would have been a 2x squared. And so this would have been a 2. And so now what do we get? We get 2 plus negative 1. That gives me 1 minus a fifth. That gives me 4/5 times pi. Okay. Now, again, this is where you'll notice, right? How did I know I had the wrong answer? I got a negative answer for the volume. That can't possibly be correct, right? So I knew I had to have made a mistake. That forced me to go back and check my work. I know for myself that if I've made an error, it's probably in some algebra somewhere. So I went back and checked the algebraic part there, and sure enough, found my mistake. Again, now in this case, we see another one where our cross sections are washers. We need to find the inside and outside radii. But again, it's again a volume by slicing, right? When you slice and you have these consistent cross sections, it's very easy, or very straightforward anyway, to find the volumes. Now, the other thing I'll mention, and then we'll have a quick knowledge check, is that the integral you end up with, in these examples, I've really focused on just getting the setup and not having the integral be too difficult. But it is possible that your integral could turn out to be something that's a little bit tricky that may require one of our other integration techniques. So you may end up with an integral that requires a u substitution, or integration by parts, or a trig substitution, right? So what I've really focused on in this video is setting up the integral, right? But once you have the integral set up, right, then all the integration techniques are now also fair game. So don't be surprised if you see one on the homework where you set it up, and now to calculate the integral, you actually need to do a u substitution, or a trig substitution, or integration by parts. All right, now to finish things up, let's do a quick knowledge check. So in this knowledge check, I'm not actually asking you to find the value of the integral. I just want you to set up the integral to find the volume of the solid of revolution created by revolving the region bounded by the graphs of y is equal to 2 times the square root of x, the y-axis, and y is equal to 4 about the x-axis. So what I first want you to do, again, just sort of work through the steps, sketch the region, try if you can to sketch the solid of revolution, think about what the cross sections will look like, find the volume of one of the cross sections, and then use that to write down your final integral that gives you the volume. Okay, great. So if I'm looking at this problem, first thing I have to do, of course, is sketch my region. Okay, so I have y is equal to 2 square root of x. See, that looks like that. I have the y-axis, and there's the y-axis, and I have y is equal to 4. Should be a horizontal line. There we go. Okay, so the region I'm looking at fundamentally looks something like this. Okay, and now I'm going to rotate that about the x-axis, right? So I'm going to rotate about the x-axis here. I can start to see, right? I'm going to get one of these sort of bowls, but now maybe the bowl is sort of turned on its side, right? And so I think about here, when I rotate this, I'm going to get something that looks like this when I rotate it around, right? Okay. All right. I'm going to take slices perpendicular to the axis of rotation. So I'm going to take vertical slices here. And now this slice, right, is going to look like a washer, but on its side. Okay. So since it's a washer, volume of that washer is going to be pi outside radius squared minus inside radius squared times height. And since I'm taking vertical slices, my height is like a little slice of the y-axis. Sorry, a little slice of the x-axis is going to be dx. So my height here is going to be dx. Okay. Now I need my radii. Okay. So my axis of rotation is here. My inside radius will be this height. This is the curve, 2 square root of x. So my height here is going to be 2 square root x. And so the distance from here to y is equal to 0, right, is just 2 square root x. So my inside radius will be 2 square root of x. My outside radius, right, is actually always this horizontal line, y is equal to 4. My outside radius is always 4. So the volume here, this will be pi outside radius squared minus inside radius squared times height. And again, I can do a little cleaning up here. Let's see, this is pi times 16 minus 4x dx. And so now to write the integral for my total volume, that's just the integral of pi times 16 minus 4x dx. Okay, and I do need to worry though, right? So be careful later on if you're asked to do this. It's not complete without the limits of integration, right? So I'm integrating with respect to x, and I should ask myself, well, over what range of x values am I integrating? Well, I'm integrating from certainly from x is equal to 0, because the y-axis is one of my bounds. I'm integrating all the way out here. This is where y is equal to, out here, this is where y is equal to 2 square root of x intersects y is equal to 4. So it's where 2 square root of x is equal to 4, where square root of x is equal to 2. So it's where x is equal to 4. So our integral will be complete now when we put our limits of integration from 0 to 4. Okay, and in fact, you can go ahead and compute this if you want. It's not terribly difficult to compute, but what I want to emphasize, and I hope I've emphasized in this video, are the geometric ideas which lead us to writing down an integral for this total volume. Once we have an integral representing the total volume, you can use the skills that you've developed in the methods of integration section to actually calculate these volumes.